Grounding requirements from the power company state that 2 ground rods are required for services in addition to other grounding methods. Therefore, you need 2 ground rods. Connecting the panels continuously and then to 2 ground rods will not satisfy the requirement. Since the panels are 200 amps, you can use number 4 bare copper to ground them. Number 4 bare copper is rated for 230 amps, which is sufficient for a 200 amp circuit. Since the panels are within 3 feet of the meter base, there is no need to install main disconnects outside. When installing ground rods, the National Electrical Code, or NEC, specifies the minimum size and type of grounding electrode conductor. For a 200 amp service, a number 4 copper conductor is typically sufficient when connected to ground rods, concrete encased electrodes, or ground rings. However, local amendments to the NEC or utility company requirements may increase this size. The NEC also outlines the requirements for the ground rods themselves. They must be at least 8 feet in length and installed at least 8 feet apart. The rods should be driven into the ground vertically, but if rock bottom is encountered, they can be buried horizontally at a depth of at least 30 inches. When dealing with multiple panels fed from a single meter base, it is crucial to ensure each panel is properly grounded. The grounding electrode conductor should run from the meter base to a grounding bus bar in each panel. From there, individual equipment grounding conductors connect to the bus bar and run to each circuit within the panel. This creates a low impedance path for fault current to return to the source, tripping the circuit breaker or fuse and clearing the fault. The NEC also addresses the bonding of metallic components within the electrical system. This includes bonding the metal enclosures of the meter base, panels, and any metallic conduit or piping. Bonding ensures that all metallic parts are at the same electrical potential, reducing the risk of electric shock. The bonding jumper should be sized according to the size of the service entrance conductors as outlined in NEC Table 250.102. When installing a grounding system, it is important to consider the soil conditions. Soil resistivity can affect the effectiveness of the grounding electrodes. High soil resistivity can impede the flow of fault current to ground, increasing the risk of electrical shock. In areas with high soil resistivity, it may be necessary to install additional ground rods or use ground-enhancing materials to improve the grounding system's performance. The NEC also provides guidelines for the protection of grounding electrodes. Ground rods should be protected from physical damage by encasing them in conduit or other suitable materials. The grounding electrode conductor should also be protected from damage by running it through conduit or securely fastening it to the building structure. When working with electrical systems, safety should always be the top priority. Always energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Grounding is a critical aspect of electrical safety. A properly installed grounding system can protect people and property from electrical shock and fire hazards. By following the NEC guidelines and local utility requirements, you can ensure that your electrical system is properly grounded and safe. Understanding the ampacity of conductors is crucial for safe and efficient electrical installations. Ampacity refers to the maximum amount of continuous current in amps a conductor can carry without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its size, material, insulation type, and installation conditions. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors based on these factors. These tables are essential for selecting the correct conductor size for a particular application. Conductor size is a primary determinant of ampacity. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. The NEC specifies conductor sizes using American wire gauge, or AWG. Smaller AWG numbers indicate larger conductors. For example, a number 4 copper conductor has a higher ampacity than a number 12 copper conductor. The material of the conductor also affects its ampacity. Copper and aluminum are the most common conductor materials. Copper has a higher conductivity in aluminum, so it can carry more current for a given size. However, aluminum is less expensive and lighter than copper, making it a suitable choice for some applications. When using aluminum conductors, it is important to select the correct size and terminations to ensure a safe and reliable connection. Conductor insulation type also plays a significant role in determining ampacity. Different insulation types have different temperature ratings. The higher the temperature rating, the more current the conductor can carry. Common insulation types include THHN, THHW, and XHHW. THHN insulation has a temperature rating of 194 degrees Fahrenheit, while XHHW insulation has a temperature rating of 194 degrees Fahrenheit in dry locations and 167 degrees Fahrenheit in wet locations. Installation conditions can also affect a conductor's ampacity. Conductors installed in free air have a higher ampacity than conductors installed in conduit or cable trays. This is because conductors in free air can dissipate heat more effectively. The NEC provides adjustment factors for conductors installed in different conditions. These adjustment factors must be applied to the ampacity values listed in the NEC tables. When multiple conductors are bundled together, their ampacity must be derated. This is because the heat generated by the conductors can build up, reducing their ability to dissipate heat. The NEC provides derating factors for different numbers of conductors in a bundle. These derating factors must be applied to the ampacity values listed in the NEC tables. When selecting conductors for a particular application, it is important to consider the load requirements. The conductor must be able to carry the continuous load current plus any non-continuous loads. The NEC specifies that the conductor ampacity must be at least 125% of the non-continuous load plus 100% of the continuous load. For example, if a circuit has a continuous load of 20 amps and a non-continuous load of 10 amps, the conductor ampacity must be at least 20 amps plus 1.25 times 10 amps, which equals 32.5 amps. Therefore, a number 12 copper conductor with THHN insulation, which has an ampacity of 30 amps, would not be sufficient. A number 10 copper conductor with THHN insulation, which has an ampacity of 35 amps, would be required. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. The overcurrent protection device must be sized to protect the conductor. The NEC specifies that the overcurrent protection device must not exceed the conductor ampacity. However, there are some exceptions to this rule. For example, if the conductor ampacity does not correspond to a standard overcurrent protection device size, the next higher standard size can be used, provided that the conductor is not supplying receptacles for cord and plug connected portable loads. Voltage drop is another important consideration when selecting conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors that are large enough to carry the load current without excessive voltage drop. The NEC provides formulas and tables for calculating voltage drop. When installing conductors, it is important to follow the manufacturer's instructions and the NEC guidelines. Conductors should be properly supported and protected from physical damage. Terminations should be made with the correct tools and techniques. Loose or corroded terminations can cause overheating and arcing, which can lead to fires. Regular inspections and maintenance of electrical systems are essential for ensuring safe and reliable operation. Conductors should be inspected for signs of damage such as cuts, abrasions, and corrosion. Terminations should be checked for tightness and corrosion. Overcurrent protection devices should be tested to ensure they are functioning properly. Understanding the ampacity of conductors is crucial for safe and efficient electrical installations. By selecting the correct conductor size, insulation type, and installation methods, you can ensure that your electrical system will operate safely and reliably. Always consult the NEC and local electrical codes for specific requirements and guidelines. Ensuring proper electrical grounding and bonding is paramount for safety. Grounding provides a low impedance path for fault current to return to the source, tripping the overcurrent protection device and preventing electrical shock. Bonding connects all metallic parts of the electrical system together, ensuring they are at the same electrical potential, reducing the risk of shock. The National Electrical Code, or NEC, outlines the requirements for grounding and bonding. These requirements are designed to protect people and property from electrical hazards. The grounding electrode system is the foundation of the grounding system. It consists of one or more grounding electrodes that are connected to the earth. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the minimum size and type of grounding electrodes. Ground rods must be at least 8 feet long and made of steel or copper. Ground plates must have a surface area of at least 2 square feet. Metal underground water pipes must be in direct contact with the earth for at least 10 feet. The grounding electrode conductor connects the grounding electrode to the electrical system. The grounding electrode conductor must be sized according to the size of the service entrance conductors. The NEC provides tables for determining the correct size of the grounding electrode conductor. The main bonding jumper connects the grounded conductor, typically the neutral, to the equipment grounding system at the service entrance. The main bonding jumper must be sized according to the size of the service entrance conductors. The NEC provides tables for determining the correct size of the main bonding jumper. The equipment grounding system provides a low impedance path for fault current to return to the source. The equipment grounding system consists of equipment grounding conductors, which are connected to the metal enclosures of electrical equipment, such as panels, motors, and appliances. The equipment grounding conductors must be sized according to the size of the circuit conductors. The NEC provides tables for determining the correct size of the equipment grounding conductors. Bonding is the process of connecting all metallic parts of the electrical system together. Bonding ensures that all metallic parts are at the same electrical potential, reducing the risk of electrical shock. Bonding is required for metal enclosures, metal conduit, metal piping, and other metallic parts of the electrical system. Bonding jumpers are used to connect the metallic parts together. Bonding jumpers must be sized according to the size of the circuit conductors. The NEC provides tables for determining the correct size of the bonding jumpers. The NEC also addresses the grounding and bonding of specific types of equipment, such as swimming pools, spas, and sensitive electronic equipment. These requirements are designed to provide additional protection from electrical hazards. Regular inspections and maintenance of electrical systems are essential for ensuring proper grounding and bonding. Grounding electrodes should be inspected for corrosion and damage. Grounding electrode conductors and bonding jumpers should be checked for tightness and corrosion. Electrical equipment should be inspected for proper grounding and bonding. Understanding electrical bonding and grounding is crucial for electrical safety. The size of the grounding wire depends on the size of the service entrance conductors. Table 250.66 in the National Electrical Code NEC provides guidance on the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. This table ensures that the grounding wire can safely carry fault currents back to the source. For example, if the service entrance conductors are number 2/0 copper or number 4/0 aluminum, the minimum size of the grounding electrode conductor is number 4 copper or number 2 aluminum. The grounding electrode conductor connects the grounding electrode, such as a ground rod or water pipe, to the service equipment. This conductor provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Proper sizing of the grounding electrode conductor is essential for safety. It is also important to bond all metallic components of the electrical system together. This includes metal conduits, metal enclosures, and metal water pipes. Bonding ensures that all metallic parts are at the same electrical potential, reducing the risk of electric shock. Bonding jumpers are used to connect these metallic components together. The size of the bonding jumpers depends on the size of the circuit conductors. Table 250.102 in the NEC provides guidance on the minimum size of bonding jumpers. When installing grounding and bonding systems, it is important to follow all applicable codes and regulations. The NEC provides detailed requirements for grounding and bonding. Local codes may also have additional requirements. It is important to consult with a qualified electrician to ensure that the grounding and bonding system is installed correctly. Improper grounding and bonding can create serious electrical hazards. It is also important to periodically inspect the grounding and bonding system to ensure that it is in good condition. Grounding electrodes can corrode over time, reducing their effectiveness. Bonding jumpers can become loose or corroded. Regular inspections can help identify and correct these problems before they create a safety hazard. The goal of grounding is to minimize voltage differences.